For our final project, we wanted to highlight the dynamics and control features behind the Cubli, the 3D inverted pendulum.
The Cubli is a continuous dynamic system first conceptualized by Michael Muehlebach and Raffaello D'Andrea. Its function is to utilize spinning reaction wheels in order to maintain stability in a previously unstable state. The Cubli continuously increases and decreases the angular velocity of the reaction wheels in order to create an internal torque. This internal torque can be utilized to counteract the torque applied by gravity and cause the Cubli to stand on end and maintain equilibrium. The goal is to control the Cubli to maintain asymptotic stability while standing on its corner.
The governing equations of motion involve the three reaction wheels, oriented orthogonally so their positive angular velocities form a right-handed coordinate frame. The torques applied by each reaction wheel add up to create a torque that directly counteracts the torque applied by gravity and any deviation from equilibrium. When calculating the necessary torque, it is important to note that the Cubli is rotating about its corner, and the origin of the reaction wheel frame is located at the center of mass. This affects the inertia matrices and needs to be accounted for when calculating torque.
This system features inputs, outputs, and feedback loops that are all correlated. The inputs to the system are the commands to the reaction wheel motors. Aside from constants like mass, dimensions, inertia matrices, etc., that are all used in the calculation of the desired torque, the Cubli uses this information to tell the reaction wheels to accelerate in a way that sums the torque to zero. The outputs of the system are the net internal torque and the measured Euler angles of the Cubli. These Euler angles are used to calculate the desired torque and are measured with respect to the inertial frame. These Euler angles are fed back to the system to acquire an updated measurement and new torque response.
The Cubli is constantly measuring its own state. It measures its orientation in the form of Euler angles and their rate of change in the form of angular velocity. The torques from the reaction wheels add up to counteract any angular velocity and return the system to equilibrium. Angular velocity is measured with respect to an inertial frame and undergoes two frame rotations to correspond with the wheel frame. When correcting for angular displacement, the Cubli should keep track of how quickly it is returning to equilibrium, so as to not overshoot.
Since the Cubli is continuously monitoring its own state, this information is fed through a feedback loop to maintain accurate torque outputs. To maintain this, the Cubli should utilize a PD controller. It should be monitoring how quickly it is approaching the equilibrium position to keep from passing the equilibrium orientation and overshooting. This will affect torque outputs and will keep the Cubli from overreacting and having to correct more than it should. The ideal case would be to pinpoint the perfect damping ratio and natural frequency to create a critically damped system and return to equilibrium as quickly as possible.
Here is a simplified block diagram depicting how the system's inputs, outputs, and feedback all operate. The measurements provide the Cubli with the current state and the rate of change for the state. The changing state space is analyzed and set through a gain function to create an output for the torque to the reaction wheels. This output is fed through a PD controller that adjusts the response torque to achieve a smoother return to equilibrium. These inputs and outputs are changing continuously and directly affect the performance of the Cubli.
The Cubli's performance can be measured in a few ways. First, its performance can be quantified by how quickly it returns to equilibrium. This is known as the settling time. It has been noted that the critical damping scenario will achieve the fastest return to equilibrium. This corresponds to the shortest settling time, as we would want the Cubli to return to its original state in the smallest amount of time. The performance can also be measured by looking at the average deviation from equilibrium. The Cubli should always be correcting for a changing state, but how well it maintains its equilibrium state could shed light on potential improvements. We want to maintain equilibrium without deviating from it. It would not be ideal to have the Cubli constantly shaking around and vibrating while trying to maintain equilibrium.
The Cubli performs calculations with respect to two coordinate frames, an inertial frame and the wheel frame. Gravity torques the Cubli about the point of rotation, so this torque, as well as the Euler angles and Cubli angular velocity, are all measured with respect to an inertial frame. The reaction wheel frame is related to the inertial frame via two frame rotations. First, the wheel frame is aligned with the inertial frame, and then undergoes a rotation about the inertial y-axis through an angle of 45 degrees. After arriving at this intermediate frame, the Cubli undergoes another rotation about the inertial x-axis. Keep in mind, the principal axis of the second rotation, the inertial x-axis, needs to be rotated to the intermediate frame, as the x-axis of the intermediate frame is not in line with the x-axis of the inertial frame.